happens when you build a power inductor backwards. You create the most efficient and compact power inductor in the world. That's what. Maybe you aren't an expert in power inductance technology, where it has come from, where it's going, and all the inductance in between. Lucky thing you have me. Hi, I'm Amelia Dalton, host of Chalk Talk. Power inductor technology has made a huge difference in the evolution of our electronic system designs. In this episode of Chalk Talk, Tim Shafer from Vishay joins me to discuss the history of power inductor technology, how Vishay developed the most compact and efficient power inductor on the market today, and why Vishay's extensive portfolio of composite power inductors might be the best solution for your next embedded system design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Vishay. Hi, Tim. Thank you so much for joining me.
Hi, Amelia. Nice to be here.
Great. Okay, so we're going to be diving into the story of composite power inductors today. But Tim, before we get started, can you give us a refresher on what exactly is a power inductor?
Sure, I can do that. First of all, a power inductor, at least from a Vishay point of view, is loosely defined as an inductor that has a current rating or a current handling capability of 1 amp or more. Typically, these products are going to have a footprint range of about 2 millimeters squared up to very large. So they can be 1,000 millimeters, and that may not even be enough for some of the newer, very high current. So there's really no limit on the top end. These are typically available in a through-hole or surface mount type configuration, but other terminations are available, and that could be something like a welded-on terminal or a bolt-on terminal, something like that. So most of them are going to be surface mount or through-hole. And the applications for the power inductors, they're basically going to be energy storage for DC to DC converters, and those can be boost converters, buck converters, or buck boost. And basically by that we mean in a boost converter you're taking a lower voltage and boosting it to a higher voltage. In a buck you're taking a higher voltage and converting it to a lower voltage. And a buck boost, it doesn't matter if the voltage is higher or lower, there's just one output voltage and the input doesn't matter. The other application is high current noise filtering. And typically this will occur when you have DC motors or pulse width modulated controls that will put a lot of noise onto the line. And these inductors help filter that out. And there's usually a high DC current involved in these type of filters.
Okay, great. Now, Tim, can we also talk about how these power inductors are constructed?
Absolutely. So traditionally, inductors are made by winding an insulated magnet wire onto a core of magnetic material. So some examples would be bar or rod inductors, where it's simply wire wound on a cylinder of magnetic material. These are probably the simplest and the cheapest type of products on the market that would qualify as power inductors. The next simplest inductor is what we call toroidal inductors, and this is wire wound on a ring of magnetic material. The next would be bobbin or tack style inductors, where you can see that the magnetic material is in the shape of a tack or maybe a bobbin or a spool, if you would, like a spool of thread, and the wire was wound around that spool and then terminated in a variety of different ways. These could be through hole or could be surface mount. The next is a shielded bobbin inductor. So this is basically what we talked about before, but there's another cup of magnetic material that's put over the top of it to help with magnetic shielding. And then finally, E-core inductors. As you can see in the picture, there's two halves that are core materials in the shape of an E. There are many different versions of this, and then that's slipped into a coil of wire, and then that becomes the power inductor. These are typically used in the higher current applications, and these can be surface mount like you see in this example, or they could be through hole as well.
Okay, great. Now, what about composite power inductors. Tim, how are they different and how did they come to be?
Well, that's my favorite topic. So we go back to 1995, and most of the power inductors that we talked about just previously were very large and bulky. And one of the newer top applications for power inductors was laptop computers. And I've shown a picture here of a laptop computer from the mid-90s, and you can see how it differs quite a bit from the laptop computers we have today that are very, very thin. Back then, they were very thick, and some of that was caused by the disk drives and the other components in there, but some of it was due to the fact that there were very tall and bulky power inductors to use for the DC to DC converters to run the memory and the microprocessors. So Vishay set out to develop a smaller, lower profile inductor that would outperform the products that were on the market. So we took a look at it and we said, well, let's try to build this thing backwards. So instead of winding wire around a magnetic core, we started out with a coil of wire, and then we formed the magnetic material around that wire coil. And you can see examples of that here, where we have a wire that is welded into a lead frame, and then we take iron magnetic material that's in a powder form. It's almost like beach sand, and we put it in a mold and we press it under high pressure, and then that coil is totally surrounded by that magnetic material to produce the inductor. So it sounds really simple, right? And the beauty of it is very simple, but in reality, it was a little difficult to implement because there was no equipment out there that could do this for us. So we had to develop the materials, the equipment, the processes, and all of the testing that had to go along with it that were not available at the time. The result, though, was the most compact and efficient power inductor technology in the world, and we're very excited about that. It took Vishay until about 1999 to actually refine and commercialize the manufacturing of what we now call our IHLP inductors. The I is for inductor, the H is for high current, the L and the P is for low profile. So inductor, high current, low profile, so that we could enable laptops and other type of computing devices to be smaller and thinner.
Fantastic. Now, as you said, these power inductors have evolved over time. How does what is offered today compare with the first composite power inductors released on the market?
Well, they had very humble beginnings. When Vishay first introduced the IHLP in the year 2000 to the market, we had two different sizes. We had what we call our IHLP 2525CZ and our IHLP 5050CE. And this was a 7 millimeter by 3 millimeter product and a 13 by 13 by 3.5 millimeter product. So there were only these two sizes available when we first released them. And then at the time, we only had one type of magnetic core material that we had designed for the IHLPs. Primarily, this was for high saturation and high switching frequencies because that was the target that we were looking at for laptop computers. And there were only several inductance values in each size, kind of a 1 microhenry, 2.2, 3.3. So we didn't have much of a product offering. But the performance advantages for the composite power inductor caught on very quickly, not only in the computer applications, but in many other markets as well. So today, Vishay has 10 different footprints and over 24 profiles in 5 different core materials to meet nearly every power supply requirement on the market. We provide literally thousands of options for DC to DC energy storage and high current filter applications. We even offer high temperature continuous operation up to 180 degrees C and currents over 100 amps in the IHLP package. So from the very humble beginning of 2 different sizes and values, we now literally have thousands of part numbers.
Fantastic. Now, Tim, can we take a closer look at these IHLP power inductors?
Yes, we certainly can. So this is kind of a quick overview. There's a lot of information on this slide, but it gives you an idea of what the different sizes are of the IHLP inductors. And over on the right, we see the general size of the inductor in the footprint. We go from 3 millimeters by 3 millimeters all the way up to 22 millimeters by 22 millimeters. And then also you can see that the current rating is also shown there for a 1 microhenry inductor. Now, we do make inductance values lower and higher than that, but just as a general comparison, you can take a look and see how much current each one of the IHLPs can handle. And in the center bottom of the screen, you can see the different materials we have. And you can see that there's a low original series, a low DCR series, a high temperature series, and a very high temperature series up to the 180 degrees C. Now, up in the left-hand corner is a graph of the performance of the IHLP, and this is the key that excites most engineers when they see this. If you look at that tack-style ferrite inductor shown in that graph, it has a saturation characteristic shown by the red line. So what we're saying is as you increase the DC current on a ferrite inductor, it gets to the point where the inductance drops very quickly and basically becomes useless. With the IHLP inductor, we eliminate that hard saturation, and we just have a very slow and gradual decline as you increase the DC current. The other advantage here, too, is the IHLP is thermally stable. So that saturation curve does not change over temperature, whereas the ferrite material actually gets worse.
Okay, so Tim, is the IHLP the only style of power inductor?
No, it's not. We didn't stop with just the IHLP. We understood that the value of this composite technology was very useful to the design engineers, so we've developed many variants over the years. First one of those variants might be an IHLD, and you can see here that this is 2 IHLPs in one package, vertically mounted. These are typically used in Class D amplifiers where 2 inductors are needed for each portion of the circuit. So some Class D amplifiers need as many as 64 IHLP inductors, and that takes up a lot of board space. So by putting them vertically, we can reduce the board space by over 50%. So this has become a very popular product for us in the IHLD configuration. We also make another inductor called our IHCL, and you'll see from the picture that this has 4 terminals instead of 2, so there are 2 separate inductors in this package as well. But where the Class D amplifiers are designed to be 2 completely separate inductors, these inductors are actually coupled. That means that their flux interacts with each other, and the interaction of the flux helps with certain type of circuits like the SEPIC converters, which are the buck-boost type converters. And so this is a product specifically designed for those type of applications. We've recently come out with our IHSR. This is an ultra-low DCR version of our IHLP, typically used in multi-phase DC to DC converters at very high switching frequencies around 1 megahertz. And there might be as many as 10 or 12 of these in a server. And so they want very high current and they want very low loss. We also took the IHSR concept and we put it into a vertical mount version. And with this vertical mount, the designers can not only save board space on their servers, but they can also get additional cooling because there is typically airflow across the server, and this gets the inductor up in the air to where it can more easily pull the heat out of the inductor. And one of my favorites is our IHLE. This is an IHLP with an integrated E-shield to reduce radiated EMI up to about 20 dB. Now this is really exciting because EMI is one of the things that many engineers struggle with when they're trying to release their product to the market, that they have to pass certain EMI restrictions, and that can sometimes be difficult. The IHLE can help with that. Then we have the IHLG, and this is gold terminations. So we take the IHLP, and instead of having 100% tin terminations, we put on gold. And gold is typically used when you have a silver epoxy attach system mainly for very, very high temperature applications that use ceramic PCBs.
Okay, so Tim, can we take a closer look at that IHLE? What does that one look like under the hood?
Okay, that one is really exciting, as I said before. So you can see in the slide here that the IHLE consists of the hood, if you will, as you called it, or what we call it is the shield, that's placed over the top of the IHLP, and then the shield is formed under so that you have two additional contact points on your printed circuit board. And those contact points typically are grounded, and that's what helps to reduce the EMI along with the shielding characteristics. So you can see in the cutaway view below that the shield completely covers most of the inductor, so it'll keep the radiated EMI at bay. And then you can also see that there is a very small insulation in between the shield and the IHLP, because typically we put those on at ground level, and so that extra insulation helps protect the IHLP inductor from the ground level signal.
Okay, so Tim, what does this IHLE power inductor buy me as an engineer?
First of all, the improved EMI can be reduced by up to 20 dB because of the E field shield. All inductors have a B field, and the IHLP is very good at keeping the B field inside of the inductor because the powdered iron material totally surrounds the coil. So typically, the B is not the problem when it comes to radiated EMI. All inductors emit some type of an E field. If they didn't emit an E field, they would be more like a capacitor. So we need to keep that E field inside, so we put this E field shield around the outside. Another name for it sometimes is a Faraday shield. So the idea here is that by putting the shield around just the inductor and not the whole portion of the circuit, which is normally what engineers have to do, this can eliminate the need for that costly and bulky Faraday shield that they might use to cover many other of the components. And as I said earlier, it reduces the E field by as much as 20 dB at 1 centimeter, and this is very significant for engineers. Currently, they're available in any IHLP value in a variety of sizes. We have the IHLE 2525, 3232, 4040, and 5050 sizes available now, and we'll have the IHLE 2020 available in Q1 of 2022. But one thing I wanted to point out here that's very exciting is that if an engineer thinks that he might have EMI problems, what he can do is he can lay out the PC board to have the extra terminations of the IHLE. And then if he needs the IHLE's EMI reduction, he can populate the board with an IHLE and everything is fine. But he can also populate the board with an IHLP that's the exact same footprint and the exact same performance. So if he doesn't need the extra EMI reduction, then he can use the less expensive IHLP in its place.
That makes sense. Now, Tim, what if I need different mounting configurations or high current? Do you guys have other options for me?
Of course we do. So we looked at through-hole high current options as well because customers wanted them. So what we did is we ported the technology to a through-hole or even other alternative mounting configurations. And this opened up the door for even higher current operation up to 300 amps. So one of those products is what we call our IHTH, and TH means through hole. And this can replace those toroid inductors that we showed earlier on, and they can replace with the same performance in half of the size. And we currently have these available in 3 sizes from 19 millimeters in diameter up to 38 millimeters in diameter. The next product we have utilizes flat wire, and you can kind of see there what it looks like on the inside. The flat wire is wound, and then the powdered iron material is molded around the outside, and we can get up to 300 amps in a 50 by 50 millimeter package with this configuration. And there are multiple termination options for this. We can make these through hole, One, we actually have holes in there that the customer can bolt on. They can be solder terminated so that the customer can either solder to them or put them in a PC board or even weld to the termination. So a very flexible design and kind of a unique shape.
So, where are these IHLPs being used today?
Well, one thing we're very proud of is in other places in our solar system. We have a line of space grade IHLPs that are specifically designed to go into space grade applications. The most popular application right now is the LEO or low Earth orbit satellites, and they go in the DC to DC converters. But as you can see here in the photo, we actually have one of our space grade IHLPs in the Mars rover that has just been in the news in the last few months. So we're very excited to see that there. But otherwise, more earthly type applications are going to be DC to DC converters in automotive applications, in computing, Internet of Things, industrial, many other applications like that.
Very cool. Now, Tim, speaking of automotive designs, with all of those benefits, it would make sense to me that these IHLPs would be a great fit for the automotive market.
They certainly are, Amelia. Vishay first entered the automotive market with the IHLP in 2002 after several years of success with our standard leaded and surface mount conventional inductors. Like you say, it was a perfect application because these are very robust products. They're easily able to handle all of the AEC Q200 standards, including shock and vibration. We can withstand shock out to 50 Gs and even more on the IHLP product. A very large percentage of our IHLP sales is to the automotive market because these are so very robust. Currently, there are many applications in both internal combustion engines and electrical vehicle applications for the IHLPs. And these are DC to DC conversion that might be in start-stop circuits, for LED drivers, automatic braking systems, all the ADAS type products, headlamps, fan control motors, transmission, infotainment, many other applications as well, as you can see on the screen. So the important thing to know here is that Vishay focuses on quality, innovation, and performance for this type of product, and that's exactly what's needed in the automotive market.
Okay, so Tim, with so many options, where do I start my composite inductor design? And where is this technology headed in the future?
That's a very good question. So many IHLX, if you want to call it that, options can make choosing the best inductor rather daunting. So Vishay has web tools that help the customer choose the best inductor for their application. One of those tools is what we call our online core loss calculator, and it can be found on our website. And all the designer has to do is enter the voltage in, the voltage out, the switching frequency, the ambient temperature, and the inductor current, and it will spit out the actual parameters of the DC to DC converter. And you can see an example of what the printout looks like on the right-hand portion of the screen. And it outputs ripple current, core loss, copper loss, and temperature rise. So the engineer can simply click around and choose different options for size, inductance, and different material and find the best solution for his application. So as far as coming soon, we're having another tool on the market that takes this core loss calculator to the next step, and it will go out and rather than have the engineer go through and try to pick the right inductor on his own, this tool will choose the best inductor from all of the thousands of parts that we have based on the same inputs that we put in above. Another exciting new tool that will be coming out early next year is temperature rise and a current extension calculator for the IHLPs for use in cold plate applications. And then we're going to have the smallest IHLP product releasing in Q1 of 2022. This is going to be down to 2.5 by 2 by 1 millimeter. And that's smaller than the 3 millimeter by 3 millimeter we talked about earlier in the presentation. And finally, we have a new lower loss material that's specifically designed for high ripple applications that you might see with the new gallium nitride circuits or the silicon carbide applications, where typically switching frequencies are around 150 kilohertz and there's a very, very high ripple.
Excellent. Well, Tim, I think that's all I have time for today. Thank you so much for joining me.
Well, it was my pleasure, and I hope that you learned a lot about composite inductors today.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Vishay. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or check out YouTube, youtube.com/EEJournal.